Thank you. So yeah, this is joint work with Tully Kaufman. So to start, I'll just give a brief recap, a brief intro on quantum LDPC codes, because everything I'm going to talk about is based on them. So in quantum error correction, we typically start with some k message qubits, like logical qubits, which we encode into some n-qubit physical state, such that if some number, say at most d of these physical qubits, are corrupted or erased, if we somehow lose them, then we can perform some stabilizer measurements to recover the original message. And the key point with this LDPC property is that these stabilizer measurements are all low weight, or like constant weight measurements. So maybe we measure, say, these, say this Pauli X, just the tensor product of these three Pauli X's, maybe these three, and then some Z's, and we measure a lot of low weight stabilizers like this. And after doing all these measurements, we can recover the original message. So this is just the general error correction paradigm using quantum LDPC codes. And motivated by this, there's been a long line of work in quantum LDPC codes trying to improve the parameters, which accumulated in this construction of asymptotically good quantum LDPC codes. First by Panilev and Kalichev, and then there were some additional works that modified and improved and simplified their construction. And so these are just codes that have constant rate. So there's only a constant factor overhead in the number of physical compared to the number of logical qubits. Constant relative distance, so you can recover from a linear number of errors. And constant locality out, so all the stabilizer measurements are constant weight. Now, the construction of these codes was a major breakthrough for error correction. And somewhat surprisingly, it seems like they've also led to major breakthroughs in complexity theory. So I'm sure many of you see where this is going. There was this breakthrough result on NLTS Hamiltonians from good quantum codes a couple of years ago, which showed that the Hamiltonians associated to these asymptotically good codes are NLTS. So there's some circuit lower bound for constructing low energy states for these Hamiltonians. And I'll later get into what this exactly means. But some people may not be familiar with the fact that there was actually a prior complexity theoretic breakthrough also using these codes just a few months before by Hopkins and Lin. And this is actually an application to classical complexity theory. So they showed explicit lower bounds against a linear number of levels of the sum of squares, the SoS SDP hierarchy. This is like a very classical, a very powerful classical algorithmic framework. And they showed how using these asymptotically good quantum LDPC codes, you can actually get lower bounds or hard instances for this classical algorithmic framework. So these were two major breakthroughs in complexity theory based on these codes. And in this talk, I'll describe a couple of maybe relatively modest, but a couple of improvements to each of these results. So for these explicit SOS lower bounds, I'll show how we can make them strongly explicit in the sense that while these lower bounds were explicit, so they gave like a polynomial time algorithm to compute a hard instance for SOS, they were in like a very technical sense weakly explicit. So it's not like they just wrote down a hard instance. You need to do some computation to find this hard instance. And we address this shortcoming. And then in actually using a somewhat related idea, or actually somewhat related techniques, which I'll get into, we also obtain NLTS Hamiltonians from linear distance quantum codes. So as I mentioned previously, the NLTS Hamiltonians required good quantum codes, meaning constant rate, distance, and locality. We remove the constant rate requirement. So we allow for codes of arbitrarily small positive dimension. So these are our two main complexity theoretic contributions. And it turns out that along the way we get some new codes, or slightly new codes. We get these things that we call planted quantum LDPC codes, which are essentially quantum LDPC codes where we plant a particular non-trivial code word in the code. So these have linear distance, positive dimension, and constant locality. But the key point is we guarantee positive dimension without resorting to parity check counting. What I mean by that is that typically if we take a quantum LDPC code with, say, n qubits, then the dimension, or the number of logical qubits, is always at least the number of physical qubits minus the number of stabilizers. This is what I refer to as parity check counting. And this is kind of how all the previous good quantum LDPC codes were shown to have positive dimension. We show that you can actually do away with this technique and instead just plant a single non-trivial logical qubit. So I guess 1 seems a lot worse than what's potentially linearly large here, but the point is we're giving a fundamentally different technique for showing positive dimension. And I'll describe how we actually use this to get our strongly explicit SoS lower bounds. But first I'll go into more on our NLTS results. So as I mentioned, this is getting NLTS Hamiltonians from linear distance, but potentially just one-dimensional quantum LDPC codes. Now the motivation for this problem comes from looking at the study of hardness with local Hamiltonians. So if we think of local Hamiltonians as kind of a mountain, where as you go up it gets harder. So somewhere in the middle or closer to the bottom on this picture are NLTS Hamiltonians, where to construct low energy states, you need super constant circuit depth. So constant depth circuits cannot construct low energy states. Meanwhile, closer to the top, up at the top, we have quantum PCP Hamiltonians, where it's QMA hard to compute even an approximation of the ground energy. So this is a much stronger notion of hardness. And indeed, implications point down the mountain. So assuming the commonly believed conjecture that QMA is not equal to NP, then every quantum PCP Hamiltonian family is also NLTS. So in kind of trying to go up this mountain, there was the breakthrough result by Anshu Breukman-Nurki in 2022 that got the first known NLTS Hamiltonians. And this was important progress towards what's a very big open goal of getting quantum PCP Hamiltonians. This is like the quantum PCP conjecture that these Hamiltonians exist. And what we do in this work is kind of, we go sideways. So we give more NLTS Hamiltonians. We give relaxed conditions under which you can get NLTS Hamiltonians. And I guess this can still be kind of viewed as progress towards the ultimate goal of quantum PCP. If you think like, well, kind of the more constructions of NLTS Hamiltonians we have, the more flexibility we have in finding a construction that might generalize or give something harder and help move up this mountain. So that's the high-level motivation for why we're looking at kind of relaxing conditions under which we have NLTS. I should briefly just formally state what is an NLTS Hamiltonian. So a family of local Hamiltonians is NLTS, or has no low-energy trivial states, if it's an infinite family of Hamiltonians normalized between 0 and 1, such that there exists a positive constant epsilon, for which as n goes to infinity, you need super constant circuit depth to construct any epsilon low energy state of these Hamiltonians. So low energy states need super constant circuit depth. They cannot be constructed with constant depth circuits. Now, how are we going to show these circuit lower bounds that we want? Well, the approach that was taken originally earlier by Elder and Harrow, and then kind of further built upon by this ABN paper, is that you can get circuit lower depths from a notion of well-spreadness. So if we measure some state rho in the z basis, so like in the standard computational basis, we get some measurement distribution of n bit strings, represented by this box here. And let's say that there's, say, some region here and some region here, such that inside each of these regions, we have a constant probability when we measure rho in the standard basis of landing inside this region. And let's also say that these two regions are separated by a Hamming distance, a linear Hamming distance with respect to the number of qubits. So this is what we call like a well-spread distribution, because there's kind of these two far apart clusters where it's like pretty likely that our measurement lies in either of these two far apart clusters. So if rho has this property, if its measurement distribution has this property, then it turns out that any circuit constructing rho must have at least logarithmic depth. So no constant depth circuit can construct rho. And what this says, to get NLTS Hamiltonians, we just need to show that all the low energy states are well spread in this manner. If they are, then we get this circuit lower bound. Now, what local Hamiltonians have low energy states that are well spread like this? Well, again, going to the Elder-Harrow and the ABN work, it turns out that quantum LDPC code Hamiltonians are very well suited for this purpose. So now just a bit more background on quantum LDPC codes. Here I've drawn the code qubits in the middle. We have X stabilizers on the left and Z stabilizers on the right. So every of these boxes here represents an X stabilizer where kind of the incident qubits correspond to the Pauli X's that this stabilizer applies. Same with Z stabilizers, and you can see that kind of this Pauli X, the tensor product of these four X's with these four Z's, these two operators commute. And indeed, all the stabilizers need to commute in a stabilizer code. So the dimension, the number of logical qubits in this code, is the number of qubits minus the number of stabilizers. We define a logical operator to just be any operator that commutes with all the stabilizers but is not itself a stabilizer. So here's an example of a logical operator. And the distance of the code is the minimum weight of a non-trivial logical operator that's not a stabilizer. So this code is distance 2. And the locality is the maximum weight of a logical operator. Now the code Hamiltonian is the average of an X and a Z Hamiltonian, where the X Hamiltonian is an average over all the stabilizers of 1 of the identity minus that stabilizer divided by 2. And the same for the Z Hamiltonian. So essentially our final code Hamiltonian H is basically an average of a number of terms. Each term corresponds to a stabilizer, where that term basically enforces that stabilizer. So for instance, code states, which are stabilized by all the stabilizers, have energy 0 in this Hamiltonian. And if we take some very high error state that violates all the stabilizers, it will have energy 1. So the Hamiltonian's energy measures kind of how many errors have occurred, how many stabilizers are violated. Right, so I can now kind of state these, I guess, what's known about QLDPC code Hamiltonians and whether or not they're NLTS. So Elder-Harrow in 2017 showed that if a quantum LDPC code has linear distance, positive dimension, so any positive dimension, and something called local testability, then the associated code Hamiltonians are NLTS. But unfortunately, there's no known codes that satisfy these three properties. And the reason here is that this property of local testability is very strong. It says basically that kind of this code Hamiltonian I described, in addition to measuring how many stabilizers are violated, also measures how many errors you've had. And the two are kind of linearly related. And we still don't know how to get codes that have local testability and linear dimension. So Anshu, Broikman, Nurki resolved this shortcoming by showing that codes with linear distance, linear dimension, and a weaker notion of testability called clustering do yield NLTS Hamiltonians. And all the known quantum LDPC codes prior to their work satisfied these three conditions. Or all the known good, like asymptotically good quantum LDPC codes. So in this work, we get the best of both worlds, because you can see that the ABN paper had this added constraint of linear dimension, whereas Elder-Harrow originally had just any positive dimension. And so we show that linear distance, any positive dimension, and this clustering property, like this weaker notion of testability, together yield NLTS Hamiltonians. And as I mentioned, we at the start, we introduced these like planted quantum LDPC codes, which basically give codes that likely have positive dimension but not linear dimension. So we also get some, I guess, slightly new codes that also give NLTS Hamiltonians. So I don't have time to give the whole proof. I'll just try to highlight the key point. The key point is this uncertainty principle. So in general, if we measure an n-qubit state row in both the x and the z bases, and each of these boxes represents like f2 to the n, the set of all n-bit strings, then we can ask whether we can kind of know very precisely where the measurement will lie in both the x and the z bases. Say we have a set S in the x basis and a set T in the z basis, such that with very high probability, an x basis measurement of rho lands in S and a z basis measurement of rho lands in T. Now, uncertainty principle intuitively says if these sets are small enough or specific enough, we can't know that the measurement will likely lie inside either of these. Kind of in one of the two bases, there has to be some uncertainty in where the measurement will land. And the specific uncertainty principle that Elder and Harrow used is that if S and T are eigenspaces of anti-commuting logical operators, then kind of we cannot know that the measurements will lie inside either of these sets. Whereas the ABN paper used a different uncertainty principle. They just said kind of as long as the product of the sizes of these sets is sufficiently small, as long as these sets are sufficiently small, we can't know that the measurement will always land inside them. Now, Elder Harrow established this condition of these logical operators using local testability. Andrew Borgman-Nurki established, like they got these small sets using a combination of linear dimension and this clustering property. And so at a high level, what our contribution is showing that this clustering property alone is sufficient to finding these anti-commuting logical operators in these sets S and T where we can apply the uncertainty principle and get well spreadness in either the x or the z basis. I guess intuitively what's going on is we're showing that the low energy states of quantum LDPC code actually respect the structure of logical operators. And by showing that, we're kind of able to relax the local testability that Elder Harrow used, which really says, I guess they use this local testability to show that low energy states correspond to true code states. We show that even though there may not be such a precise correspondence, low energy states still respect the logical code operators. Oh, so I just told you that we can get away with low rate for our quantum LDPC codes and still get NLTS Hamiltonians. Do we even know of any codes that have low rate but still linear distance in our LDPC? It turns out that we can construct such codes, or at least probably construct such codes. We can construct codes, quantum LDPC codes of linear distance, where we can only bound the dimension by 1, though we can't prove that they don't have higher dimension. At least we don't know how to do that yet. So the quantum argument's a bit more complicated than the classical one, so I'll just give the classical intuition. The idea here is if we take an expander graph and some constant size inner code, C sub n, then we can always construct a Tanner code C, where code words are simply assignments of edges to bits. And the constraints for these code words is that every vertex sees an inner code word. So for each vertex, its view, like the bits it sees on its edges, form a code word of the inner code Cn. Now, to ensure positive dimension for this code, the standard method is to count constraints, because we have kind of, each constraint is a linear equation. We have some number of bits, of code bits, some number of constraints from these vertices and these inner codes, and if there's more variables and constraints, then kind of there's some degrees of freedom which give code words. But an alternative thing we can do is literally just require that the all ones vector lies in the inner code. Because then the all ones vector also lies in the global code, because every vertex, its local view, consists of all ones. So now it doesn't matter how many constraints we have. We could have an arbitrarily many number of constraints. These inner codes could be anything, but as long as they contain the all ones vector, and I guess also the all zeros vector, we have a non-trivial code word in the global code. So we do this quantumly. Some things get more complicated, but intuitively, This is all we're really doing. Now, where are these codes useful? At a high level, they avoid parity checking, as I mentioned earlier. So like there's some classical applications where potentially this might eventually, I guess it's nice to have in the back of your mind that you can always do this, maybe if parity check counting doesn't work. But more concretely, we use it to get these strongly explicit SOS lower bounds. So just very briefly to conclude, what is an SOS lower bound? Well, the sum of squares hierarchy is a very powerful classical algorithmic framework. So this is actually back to kind of putting our classical hats back on. And because it's such a powerful algorithmic framework, we want to understand its limitations. And yet basically all known hard instances prior to the Hopkins-Lin work were randomized. So we couldn't like explicitly write down a hard instance for this hierarchy, for these algorithms, until the Hopkins-Lin result. But these were only weakly explicit, in the sense that they needed Gaussian, they constructed these hard instances for SOS using quantum LDPC codes, and they needed Gaussian elimination to find a non-trivial code word in a quantum LDPC code. So they need to do this like long polynomial time calculation to find a non-trivial code word just to get this hard instance. And we resolve this, we get like strongly explicit hard instances for SOS by just using these planned quantum LDPC codes. Because intuitively, they give CSS codes where the X and Z codes contain the all ones vector. So you don't need to do any looking for any sort of search to find a non-trivial code word. You just take the all ones vector. So that's kind of the idea of how we get these strongly explicit lower bounds. So that's just about it. Just to wrap up, our three main contributions are NLTS Hamiltonians from low rate codes, the planned quantum LDPC codes, and we use those to get strongly explicit SOS lower bounds. So thank you.
Okay, thank you for a great talk. If people have any questions, if you want to come up to the middle of the room and line up behind the microphones.
Hi, thank you for the great talk. What is a significant difficulty in proving the rate of these planted QLDPC codes? Because usually the analysis would just say, oh, I sampled the local codes to have these particular parameters, and then that would push that to like the global code. But so what's the difficulty here?
Exactly. So we can definitely, like you said, I think what you're saying is we can get constant rate for these.
Right. Like why can't we prove like constant rate, but instead we don't know its rate?
Exactly. So we can prove constant rate
Mm-hmm.
just by what you're doing, setting parameters so that we count parity checks and get constant rate.
Mm-hmm.
What we can't do is, what we can't do is show that we can have non-constant rate. So we could also set parameters in the regime where ordinarily we would have 0 rate,
Mm-hmm.
but we know that we have this one planted code word.
Mm-hmm.
We can't show that in this regime we actually have low rate, which is,
I see. Okay.
I don't know if you would want to do that, but we
I
can't prove it.
Okay.
At least I don't know how to prove it.
Thank you.
If you could find like a code that met all the conditions from the Elder Harrow paper, would that give any kind of stronger implication than NLTS Hamiltonians? Like any stronger implications towards the quantum PCP theorem? Or is like local testability kind of not as interesting now because of your result?
Yeah, I think local testability is still very interesting. I don't personally know of any concrete applications, but I think the idea of having a locally testable code where kind of low energy states correspond exactly to low error states could hopefully be useful for moving forwards. So I don't have anything concrete.
Hi, can you plant any arbitrary bit string for the planted QLDPC code?
Yeah, I don't know how to do much beyond the all ones vector. I think if you're careful, you could do some that are probably like maybe that are periodic, so that in every local view they look the same. But in general, it seems tricky to generalize.
Even in a classical case?
Yeah, like classically, I don't even know how to plant like two non-trivial code words or more than a constant number.
How about just one code word, which is not the all-one bit string in the
Sorry?
classical case?
How much is one?
No, like just one code word, which is not the all ones bit string in the classical case.
Oh, how would you do it?
Yeah.
So I think one thing you... Oh, I'm not sure. I think one thing you might be able to do is if you ensure there's enough structure with the expander graph, you could probably just make like every local view kind of have the same structure, but I'd have to check that. I'm not even sure how to do that.
Yeah, thank you.
Okay, if there's no more questions, let's thank Louis and all the speakers in this session again.